Good afternoon, ladies and gentlemen. Welcome to my presentation here at the Hightech Stage at W3 in Wetzlar. I am Alexander Telle, the CEM of ACM. We are the German subsidiary of Acktar. Acktar itself is an Israeli technology company, and we are specialized in the development and application of ultra-black light-absorbing coatings and coated foils. Let's put it like that: we are the niche within the niche of optics and photonics. There are three general applications for our products. You can use them to suppress stray light, but also to absorb laser power or to create high emissivity surfaces, for example, for passive thermal management and infrared applications. We are active in the wide field of photonics, and with that in the most of the technical markets like industrial vision and sensors, life science, analytics, medical lasers, and semiconductors, but also in space industry. Let's today talk about how to make optical metrology and industrial vision applications faster and more reliable with the help of absorbing black coatings. Based on optical key technologies and non-contact measuring systems, cameras also for infrared and sensors make an enormous contribution to monitoring the manufacturing process and efficient quality control, which is nowadays so elementary for productivity and competitiveness in numerous industries, such as automotive, medical, but also electronics and semiconductors. And the completion of inspection tasks by industrial metrology serves the quality assurance of the product and of vendor parts. What is the impact of stray light interferences in optical metrology? Reliable signal detection, even in the presence of interfering influences such as stray light and reflections, is a very important topic to cover here. Acktar's deep black coating products absorb unwanted stray light on one hand, and interferences caused by direct or reflected light in optical systems for industrial metrology. And in this way, the accuracy of signal detection and measurement performance can be maximized. The signal quality is then sufficient to ensure reliable measurement, even when measuring on dark, reflective, or translucent surfaces. The application of our black coatings or coated foils is particularly suitable for system manufacturers who place increased value on the precision, on the quality and reliability of the measurement system. Where high precision measurement results are required, our black coating solutions can realize a leap in the performance. What you typically want to achieve in vision applications is to maximize contrast in visible, but more and more important also in the infrared range. And one tremendous influence on the ability to acquire the perfect image is the texture of the surface and effects that come from that. And the surface can be very different in nature, possibly structured or textured or even shiny, reflective or transparent. And it requires a high sensitivity, a low noise, and a high contrast of the image processing system used. And this is even more true if you not only use it for imaging, but also for image classification or AI-supported systems. There are numerous examples where only a low contrast can be achieved with the usual elimination methods, such as when inspecting rubber or parts made of dark polymer materials. This circumstance makes fast and precise surface inspection and the detection of defects a major challenge for the industrial camera system. And as already said, it's not only about imaging in the visible spectrum, but more and more important, the ability to be able to achieve good image quality in infrared ranges, in near-infrared shortwave, but also in far infrared ranges. And there, not only the reflection itself can be a problem, but also different emissivities of the surfaces can play a big role to be able to see what you want to see. To summarize that, I think it's important to talk about why and when to think about scattered light and stray light at all. Many of you know that that scattered light can have a dramatic impact on the quality and performance of the optical system. And if you address this challenge, for example, with deep black absorbing coatings, you can easily positively influence the image quality, the contrast, or even the sensitivity in the system. And this at the level of the hardware, and this is, I think, most important, you start improving at the level of the hardware and not later in the image and signal processing. Taking these considerations into account as early as possible in the development process helps to clarify the necessity of scattered light suppression measures. In this way, it's possible to increase performance or to reduce the complexity of the optical setup with relatively little effort. But also later in the product life cycle, the integration of measures for stray light optimization can provide benefits, for example, a higher or more reliable image quality. But now you could say, okay, I have used like black anodized aluminium in my optical setup since decades. Why should I now invest, surprisingly, in a specific, maybe new black absorbing coating instead? Well, and this is my not too serious answer to that. It's because your application deserves a better performance than standard, and it might not only work in the visible but also in the UV or in the infrared range. If you have a look onto that diagrams that I took from a scientific paper, you see in the upper left diagram the reflectance of black anodized aluminium, and what you can specifically see, and what you can see is that black anodized aluminium turns transparent or reflecting at 650, 700 nanometers already. So that means that if you have scattered light, stray light in that wavelength range, you will have it on the sensor. It will disturb image quality and sensitivity. And also, if you think, okay, I'm just in the optical laboratory, let's take my black permanent marker. Also, this one doesn't help you. In the right diagram, you see the performance of our coatings, and here it's always the reflectance, the total reflectance, integrated reflectance on the part. And what you can see is that we guarantee highest absorption rate, lowest reflectance rate over a very broad wavelength range, starting in the UV, over the visible, into the infrared. This doesn't stop here. Well, this was what is measured, but we have measured our performance up to 14 micrometers with a very stable low reflectance and high absorption rate of around 2% in that range. Now I want to explain to you how our coating technology works and what the advantages of our coatings are. We apply our coating in a vacuum deposition process, and what we do is what you can see on the left in the ACM images. It's how our coatings work. We create a surface morphology from a composition of metal and metal oxide structures, and these lead to a high specific surface area. With that, we generate like a sliding refractive index into the coating itself, and this makes it possible to absorb light in a broad wavelength range, but also in a broad range of angles of incidence. That is why our coating is working in the wavelength range in the UV, visible, and infrared. But as it is coming from a vacuum technology, it's an inorganic coating, and with that it brings some nice advantages like high temperature resistance and durability. And another very important point is that we are able to apply our coating to most materials. We are not limited to specific alloys, stuff like that. We can apply the coating to most metals, to glass, ceramics, but even plastics. There are only two restrictions. The material must be vacuum compatible and slightly temperature resistant. As already said, it's totally inorganic, and we are qualified for few quite demanding applications like space technology, but also ultra-high vacuum environments and clean room and semiconductors. The coating itself, we will see it maybe later on, is relatively thin. For a visible range, we apply a nominal thickness below 5 micrometers. And this helps us to be able to apply the coating highly conformable to sharp edges. And in optics, especially in optomechanics, you use sharp edges in apertures and diaphragms very often, but we are also able to apply the coating to very complex three-dimensional shapes with the help of our vacuum coating process. So the most important question for you might be, how can I use it? How can I bring it into my product? How can I blacken my optomechanical components? And we have two options for you. One we call direct coating. That means we apply the coating directly to discrete optical and optomechanical components in the vacuum coating process. You either supply us your parts and we apply the coating as a service, or we also offer to purchase mechanical manufacturing of the component, apply the coating in our facilities, and deliver ready-to-use, ready-to-assemble optomechanical components. The second option on the right is coated foils. It's the same coating technology, but we have a machine that is able to apply the coating in a roll-to-roll coating process. Typically, an adhesive backing is added to this foil substrates, and we can supply you with sheets or customized pre-cuts and die cuts. As you can see in the image, it's very easy to use, but may be limited to relatively flat geometries. Also, the foils are available with like space-grade materials, and you might already know them as for a couple of years now we are part of Edmund Optics catalog mainly with our coated foil products for the optics laboratory. As I already said in the beginning, we are active in various markets and applications. Here's just a partial overview. Wherever light is generated, shaped, and detected, there's always some light that disturbs and is undesirable. Our Acktar black coatings suppress and absorb the scattered light, and with that enhance the performance of the optical system. And as you can see, there are quite demanding applications we are already serving, like space industry, laser applications, for example, beam dams, but also sensors for automotive. In medical, we are very strong in endoscope cameras and optomechanical components for endoscopes, but also bioanalytics, just as an example. And I want to show you some more parts where we have applied the coating to, also to illustrate the variety of material and the variety of geometries where we can apply the coating to, starting on the far left with a glass substrate and the structured coating. Blackbody radiator from titanium, but also typical like optomechanical components for industrial optics, like spectrometer housings, lens housings, and apertures. And what you can also see on these pictures is that we are able to apply the coating selectively. We need to hold the parts during our process anyways, and we add to these coating tools, we can add mechanical masking technology that helps to cover certain areas that doesn't need to have the coating and where you want to have for example, the bare metal. For example, to protect mechanical interfaces like threads, fittings, from the coating, but also outside areas where you might want to have another surface is possible. It's also possible to combine our coating with hard mechanical protective coatings like hard anodizations. Then you would typically anodize the aluminium part, and afterwards we apply the coating only to surfaces that are relevant to stray light and scattered light in the optical path. But we are also able to apply the coating to glass and to the structured silicon wafers, what you can see over here. And it is possible to pattern and structure our coatings as well. The simplest way to structure it is to use a mechanical mask, but it can be also done with laser engraving and with photolithographic patterning. And this can help, in this example, to increase the absorption of light and to enhance the sensitivity of that sensor element that is sitting there, but also possible to do it the way around, to cover all the electronics and to leave out the optical sensitive area, and to avoid any reflections from the non-optics area on that wafer. With that, I end my presentation also on time, but not without asking you to visit us on our booth. If you turn around, you can see it directly over there. It's the black one. You can also contact me by phone, email, or LinkedIn, and I ask you to give us your stray light problem. We want to solve it. And just a few words to the satellite image you can see over here. Fun fact, this satellite image was taken by Copernicus Sentinel-2 satellite instrument. It's an Earth observation satellite from ESA for mostly for environmental tasks. And the filter assembly that makes this image possible is the optomechanical parts of the filter assembly are coated with our coatings. And on the image you see the border between Thuringia and Saxony-Anhalt, where our location actually is. Thank you.
Thank you, Mr. Telle, for your interesting talk. Do we have questions? First from the audience, of course. Not yet. So maybe I start with one. I was wondering, you were talking about the optical properties of your coatings. Can you as well tune the electrical ones? Or have you thought about that, like electrical conductivity?
Yes, electrical conductivity is often a question, especially if you want to achieve like a conductive surface. So the nature of our coating is typically non-conductive, as it is metal oxides, but we can tune the amount of metal within the coating and can enhance conductivity with that, so that it is possible to have the coating like dissipative. So we have applications with customers where they use the coating close to electron beam applications, where you don't want to have any electronic discharge and stuff like that. So this is definitely possible. There are also applications like for testing chucks for photovoltaic applications where you want to have a higher conductivity, and this is definitely possible, yes, to also influence that.
And does this then again change the optical properties, or is it like dependent, or can you tune those properties independently?
Well, we can find an optimum, but this is, as always, if you play with one factor, you definitely change the other one. Yes.
Thank you. Do we have questions now, maybe? Okay. I don't see any. So we thank you again, Mr. Telle.
Thank you.